All right, I'll start over if that's all right. So, so we're going to learn about electromagnetic waves, and to sort of truncate and get back to where I was, electromagnetic waves have a lot of applications in science and engineering. Electromagnetic waves, different spectrum parts of the E&M spectrum help us learn about different parts of the universe. Certainly, information is encoded wirelessly. We use electromagnetic waves all the time, and the frequencies at which they're encoded are often, well, they shouldn't be, but they often cause concern. So the big one is moving to 5G, which is in that 25 gigahertz regime. And we can talk a little bit about that. And of course, how we see things, when we make sensors, how we see things or design microscopes or telescopes, all require us to understand electromagnetic waves or light. And the first thing we want to do is get a sense for what it is we see. Now, when we experience light, you'll notice that we see with our own eyes everything from red to ultraviolet in wavelength, that's 700 nanometers down to 400 nanometers. Now, I want to show you that in the electromagnetic spectrum at which we study, which goes from 10 to the minus 16th nanometers all the way to the size of the universe. 10 to the 8th meters isn't the size of the universe, but you can make radio waves that big. When you look at these very large range of electromagnetic waves, you'll notice that visible only takes up a very small portion of the electromagnetic spectrum. All right? So you'll notice when we break it down, you have your radio waves here. You have maritime and aeronautical uses for these long wavelengths, also astronomy. AM radio is here in the short wavelength, but you'll notice as we get closer to visible light, we get things like TV channels, cell phones. This near infrared area is where things like when you get to 2.5 gigahertz is around here. So 5 gigahertz is somewhere here. Your 5G is getting near here, moving towards infrared, or moving towards infrared and then towards visible. Back in the late 1800s, we only had sensors for this, a little part of the ultraviolet, a little part of the infrared and visible. But as we've, as technology advanced and science advanced in the 19th century, radio was discovered on this end of the spectrum, long waves were discovered. And then as the century came to a close and we went into the 20th century, we were able to observe nuclear decays and things like that. And that opened up this ultraviolet and X-ray region, all right? And with X-rays being discovered in the early part of the 20th century. And then as we got more powerful telescopes, we could see gamma rays. Most gamma rays mostly come from cosmic sources, so sometimes they used to be called cosmic rays. And it wasn't until fairly recently, I'd probably say in the last 50 to 60 years or so, that we could create gamma ray sources in the laboratory. So there's a lot going on with the electromagnetic spectrum. And by understanding light, we understand fundamentally how all of this works. Okay? Now, electromagnetic transmission is the main application of electromagnetic waves. That's the big one, right? If you don't believe me, pick up your phone and make a phone call. Both your cell signal works through this, and your wireless works through this as well. Some of you are probably, this is being beamed from your cable modem through wireless into your computer. All right? And so we can get a sense. It's too bad Professor Senkov and I talked for a while about trying to design a antenna. We just could never get the permission to do it. But we talked for a while about making an antenna on the roof of the M building or the E building. And so we could take students outside, so you could build your own oscillator with a battery, your own LCR oscillator, and then you could move it to the antenna. You'd have a winding for the antenna, and as you can see, with this LCR circuit, as you go through the inductor, you can use this as a transformer and induce a voltage here down the antenna and transmit at the end of this antenna traveling electromagnetic waves. All right. So our goal here is to sort of understand the structure of the electromagnetic wave. We can see that we need both LCR circuits and transformers to understand the generation of the transmitted wave. But once the transmitted wave moves, you'll notice we have these wavelengths, right? We have the directions propagating in these wavelengths. We want to get far enough away from the source so that the transmitted wave starts to look, I'm going to draw a few more, and then it'll start to look like this, right? Where the curved part is just too big. And when we get to this regime here, we're going to approximate, we're going to call this a far field because we're far from the source, and we're going to approximate these as plane waves. And approximating things as plane waves is nice and convenient because you can write the wave, you can write the propagation of the wave at least as, you know, y equals y naught e to the I kx. All right, that's one way of doing it, minus omega t. And in fact, it's easy when you do it this way to separate the x and omega t parts, the temporal and the other parts. Now, of course, we don't know enough math to really take advantage of this very simple and compact form. So what we're going to do is we're going to look at plane waves, these repeating plane waves, and we're going to find that our electric fields and magnetic fields that make up our electromagnetic waves are going to be described in terms of our cosine functions. All right? So let's see, did we already state that? No, we didn't already. There we go. Okay, that's where that happens. So let's take a look at these waves as they go by. So we can see this wave sort of propagating. Now we sort of can take this snapshot at different times along as the wave is moving. So we're imagining a wave that's sort of moving towards us, and at different times we can see how the electric and magnetic field change direction and oscillate. And I want to start at A, and I want to look at B field first. So we're going to go around this loop twice. Actually, we're going to go around 3 times. Okay? So as we go around, you'll notice that the B field shrinks, goes to 0, points the other way, it gets to a maximum, and then goes back, shrinks, starts to point the other way, and then ends up back where we started. So this is indicative of a cosine function, right? It behaves the same way. If you don't believe me, I will draw one for you. Just take a minute. Right? We start at a maximum, and we go down to a minimum, we cross, and we end up right back where we are. So this would be figure A, and this would be back to A. When we cross 0 here, this would be figure C. When we cross 0 again, that's figure G. And you can sort of see when we're completely at the opposite end, this is figure E. So I'm not going to draw all of it, but you'll notice you go A to C to E to G, and then back to A. All right? In a cosine function. So it should be obvious to you that we're going to describe both the electric and the magnetic fields in terms of either cosine or sine functions. Now, it'll just depend whether you use sine or cosine, whether you start at your amplitude here or you start at 0, right? If you start at 0, a sine function makes more sense. If you start at the maximum amplitude, the cosine function makes more sense. And then you'll go from there. So, and basically both of those functions are solutions to Maxwell's equation. But now let's go and start at A again, and let's look at E. So E gets smaller and smaller, and then it disappears, and then it points the opposite direction. I gotta get my finger up here. Right? It starts pointing the opposite direction. You'll notice it gets to that amplitude, that maximum amplitude. It shrinks, goes back to 0 again, starts to grow, and we get right back to where we started. So we can see that not only does it behave like a function, it's in a different way. It also behaves like a cosine or sine function. If we're starting at A, it'll behave like a cosine function. But again, if we start at C, it'll behave like a sine function. I think traditionally, we use sine more than cosine for E and M waves because we usually want to start at an origin. But it's not a big deal. What I want you to notice, though, is that E only changes in this vertical direction, right? And B only changes in this horizontal direction. And I want you to notice that even though they disappear here, the angle between them is always 90 degrees. Okay? And so we're going to notice that as we make some observations about our E and M waves. All right? So the electromagnetic fields E and B are always perpendicular to the direction in which the wave is traveling. Thus, the wave is a transverse wave, as we discussed in chapter 16. So as you can see, the wave, no matter which way you're going, the direction of travel will either be into or out of the board. So E and B have to stay on this plane. Now, that being said, the electric field always has to be perpendicular to the magnetic field. This is a condition of Maxwell's equations. Once we solve for the E field and B field, one of our conditions of Maxwell's equations is that these be mutually perpendicular, all right, particularly in free space. So the product E cross B always gives the direction in which the wave travels, and that's going to be important because that will give us the power delivered by the wave, or the average power. And the fields always vary sinusoidally, just like the transverse waves that we discussed in chapter 16. Moreover, the fields vary with the same frequency and in phase. That means that you'll notice that they peak together, right? So B and E both peak at the same time. They both minimize and cross zero at the same time. And then they peak again at the same time here down in figure E, or part E of the figure. So a lot of stuff to look at here, a lot of stuff to know, but we want to cover on sinusoidally. That means you can either have a sine or cosine, and we'll very quickly see here that, yeah, if it's sinusoidally varying, they're going to go with the sine function. But if you pick sine or cosine for one, you have to pick it for the other, because again, E and B are in phase. All right? You'll notice EM and BM are those amplitudes, and E and B are the values. So now, when we have this equation, we can do some massaging and use Maxwell's equations. I'll have you go over that. We talked a little bit about how to get the important differential equation, but basically you can take the ratio there and find one of the important results is that we'll have that the ratio of E over B will be equal to the magnetic field C. And basically it's because you'll look at that, you don't divide these two equations because that's not going to work. You take the time derivative of B, and you'll find that it's equal to the position derivative of X, right? So you'll have something like dE dx was minus dB dt, which if you look at it is this is a simplified form of Faraday's law, right? They're going through the same area. You can get the fields directly. So that's not so epic where that comes from. But if you take these partial derivatives and you set them equal to each other, you take the partial derivatives of these functions, you will find that you'll have things in terms of E and B, and C will be the speed of the wave, which will be and you can define the speed of the wave, right, in terms of K and omega. So if you will recall, let's see here. Hold on. If you recall here that C, or the velocity of the wave, will be equal to omega over K. And so that means C will be equal to omega over K, because these are electromagnetic waves. And you'll find when you take those derivatives that you can set this equal to E over B, no problem. All right, and this is something we'll be using to make our lives easier as we do some analysis on these waves. Now, to talk about them energetically, we already saw this result. Oh, I should have just trusted. It's right here, right? Speed of the wave is omega over K, and the speed, we already talked about this last week, is equal to 1 over the square root of mu naught times epsilon naught, which is why we maintain those permittivity constants when we talk about them. The speed of light is about 3 times 10 to the 8th meters per second, all right? And every electromagnetic wave, whether it's a gamma ray, a radio wave, or visible light, they all travel at the speed of light. There's no variance in their velocity in a vacuum, okay? There's actually really fascinating physics and implications behind a lot of that. So for instance, it used to be thought that a wave's intensity, well, we're going to see here with the pointing vector, right? Classically, we're going to be able to relate the average power to the intensity pretty quickly. So power is the rate at which energy is thrown off, and so one would think that the energy is always related to the intensity. Now, now Albert Einstein actually won his Nobel Prize by showing that the photoelectric effect, which was the energy required to shine light on and kick out an electron on a certain material, was independent of intensity. You could make a light as intense all you wanted. If it didn't have the right frequency, you couldn't kick out the photon, or you couldn't kick out the electron. Sorry. So that eventually it's shown in quantum, that when we look at quantum mechanically, that photons aren't, or that there's a quantum description of light which is discrete, that the continuous version doesn't describe. But we don't want to get ahead of ourselves yet. We want to go back here and understand that when we're talking classically, all electromagnetic radiation are waves, and they all have the velocity of the speed of light. And we'll find that their energy eventually will depend on their frequency, not the intensity or the number of particles. Okay, so what I wanted to do here is, this is a classic picture. We saw this picture, which can be helpful to see very explicitly how E and B are behaving. It's a little hard to see the wave propagating here. Here, you have to have a little bit of imagination with your X and Z, or your Y and Z axes. But you can see here that the electromagnetic wave is propagating along the X direction, okay? And you can see that here in Y, you see that E wave for the electric field, and you also see that the B field oscillates as well, and they both peak at the same time. Now, even though they both peak at the same time, it's a little disingenuous to write them the same size, because you'll recall that we know that E over B is going to have to equal C. So one of the implications there is that E is equal to C times B, or more importantly, I think B is equal to E over C. All right? So that means that if you can get an electric field of, say, 1.3 millivolts, that would be a small electric field, right? To measure the corresponding magnetic field, you'd have to divide this small number by 3 times 10 to the 8th. How's that for a small number? That's 8. You're decreasing the order of magnitude by almost 8 times. So the magnetic field is very difficult to measure, whereas the electric field is easier to measure, which is why when we talk about things in terms of electromagnetic waves, even though we admit they have both components, we very much often only look at the electrical component because it's easier to measure. That doesn't mean the B field isn't there. It must be there. Physics says it's there. It's just much, much smaller. So it would make more sense to write these as sort of, make these ones really big, so almost that you couldn't see them, and then to make these ones really small. Like that. That would probably make more sense. Okay, but this is the classic picture of an E and M wave. This is how an electromagnetic wave is constructed. All right, so any questions so far? Thoughts? Everyone's good with this stuff? Like I said, we're way ahead. If you're lost, we can work that out. I'll summarize some of this again, just in case you are, while you're formulating a question. Just remember, we're talking about the construction of an electromagnetic wave. So we can see all we've really covered here is the electromagnetic spectrum. These are just the wavelength and frequency properties of named electromagnetic spectrum, and I gave you some examples of what they could do. I won't go over those again, but that's all we're doing here for this slide. Then what we did is we looked at how to generate, using stuff we talked about, the LCR circuit and a transformer, to generate electromagnetic waves. And it's actually not terribly difficult. The important part is the antenna has to be the right size, and then we can broadcast electromagnetic waves from the antenna. That's kind of what antennas do, is they excite electrons in a material, and as those electrons get excited in the exact way that relates to the LCR circuit, you know, you can push those electrons down. They get excited and go down in energy level, and then as they do that, they emit light. So that's where the emission comes from. So we talked about that, and all we wanted to do, we then started really getting into the electromagnetic wave. I'm actually going to go here. We talked about how the E field and the B field vary in an electromagnetic wave, and we talked about their relation, their right angle relation to the way the wave is propagating, that's going into the page or out of the page. And then we also talked about the relative direction to each other, that the E and B field have to be perpendicular to each other. All right. And then all we did was look at, we defined and said that, okay, both of these will vary sinusoidally. So we're going to describe them with sine functions, even though it makes more sense to describe it with a cosine function. It's kind of a whatever. Both those trigonometric functions satisfy Maxwell's equations and the wave equation, so it's fine. But, you know, people like to start at 0 more than like to start at the amplitude. So you just have to ask yourself where you're starting. That will tell you which one you use. The important thing to note is that you must use the same one. You can't have E be a sine function and B be a cosine function. It's either sine or it's cosine. All right, and you'll notice that that's got to be true because they peak and minimize at the same time. And then all I said here is, and then all we did, and the next one is we looked at a traditional wave. This is the traditional picture you would look at in a book. And we looked and saw that the E field and the B field and the propagation direction are all perpendicular to each other. And we also pointed out that the amplitude of the electric field is far bigger than the amplitude of the magnetic field. Okay? So hopefully that makes some sense, and we can move forward to some of our more interesting parts of this. So now you'll see here, we have the Poynting vector is defined as S equals 1 over mu naught E cross B. All right. Now we can write this as equal to 1 over mu naught times E. And remember, they're 90 degrees from each other, so the sine phi here is going to equal 1, right? Because phi will always be 90 degrees. But I want you to notice that we can, instead of writing B, well, I'll write B, but I want you to notice that I can write this as equal to 1 over mu naught E. And remember what I told you, B is hard to measure. And since we know that E over B equals the speed of light, we can rewrite this as B is equal to E over C. All right? And so if we do that, we'll get that S is equal to 1 over mu naught C times E squared. Now, we want to note that the direction of the Poynting vector, S, of an electromagnetic wave at any point gives the wave's direction of travel and direction of energy transport at that point. And the time average rate per unit area at which energy is transported is the average of the Poynting vector. All right, so you'll notice it says rate per unit area at which the energy is transported. So the Poynting vector it's more correct, instead of saying the power, is the intensity. And so intensity is always equal to the power over the area. All right? So if we average, if we want to look at our intensity, it's going to be equal to the average power. And so we can look at S average is equal to I, and that's going to be equal to 1 over C mu naught E squared RMS. All right? And if you want to know where that RMS comes from, you'll want to go look back at AC circuits, and it'll explain where that happens. It's sort of a product of averaging that trigonometric sine function, and you'll notice that when you have the E part here, you square it, so you have a sine squared function, the average of which will be 1/2. So when you average it, that will add an extra 1/2 factor, and what you can look at is with the E squared, that will be basically, you know, E RMS squared equals E over root 2. So if you square this, you get E over 2. That comes from averaging that sine function, is where that half comes from. So we often look at it in terms of this this RMS value. Okay? Because when we take average, that 1/2 factor is going to come out. So you'll recall from, like, I think it was chapter 17 where we talked about intensity is the power over the area. So if you have the power of a source, we'll start looking at waves as sort of these sphericals, particularly things like air. When we look at that, E and M can be electromagnetic waves can be thought of the same way. They can be looked at as a spherical source. Well, one way to understand this, it's pretty easy to understand this, right? Because you don't see light directionally. Sometimes you do. Like with a laser, sure. But if you turn on a light in a room, it's not like one wall only gets illuminated, right? Every wall gets illuminated. So in that sense, it makes sense to look at light as a spherical wave. And so you'll notice that when you look at the area, they look at the surface area of the sphere, which is 4 pi r squared, and then they have the source, the power at the source. Okay? So questions there? Questions, answers. Bum, ba-dum, bum, bum. No, everyone's good? All right. Okay. So let's move onward and upward. So we have an example. Always a good time to do an example. So when you look at the North Star, Polaris, you intercept light from a star at a distance of 431 light years. You will have to convert that to meters. I hope you, you know, I hope you brought your Googles and things. That's how I'd probably just do that. And emitting energy at a rate of 2.2 times 3 times that of our sun, which is the power the sun emits is 3.9 times 10 to the 26 watts. Now, I don't know that we talk about this in this class, but I want you to sort of get some perspective on how much energy that is, because right now it just looks like numbers. So 3.90 watts is enough power to power all of civilization for 1 million years. And the sun outputs that much energy every second. So if you're wondering if the sun really is a renewable source of energy, it truly is, at least for beings of our scale. So neglecting the atmospheric absorption, which, by the way, you really can't. It's not a great approximation. But what you could do is, it is not a bad approximation if you put your telescope, though, say your measuring device in low Earth orbit, which is fairly easy to do, right? So if you wanted to make these measurements outside the atmosphere, you could take a sensor out. We want to find the RMS values of the electric and magnetic fields when the starlight reaches you. So I want you to, you know, we have the power, right? So we know that the intensity will be equal to, let me get there. We know that the intensity will equal 1 over C mu naught times E squared, ERMS squared, right? So we know that, and we also know that I, the same thing, equal to the power over the area, so 4 pi r squared. So things you have to do here, so I want you to give it a try, but you'll notice you have a distance, and you do have the power. But it asks you to do some sort of compound conversions. So I want you to play with that. I want you to, to take a 5-minute break from hearing me talk at the very least, and try and work out the problem and see, as always, work it out. If you have questions, that's great. We'll answer them. If you're feeling shy about it, we'll go over it, and you can try and figure out where you got lost. Okay? So take a couple minutes. At 6:40, we'll start to go over it, and see if you can figure it out. It's pretty much done for you up there already. See if you can put it together. That's just what I want you to do. And like I said, I want your brains to take a break from listening for a little bit and be a little active. That's the main goal there. Oh yes, you do. Light years to meters. You can do it by hand, like all hardcore scientists would, or you can look it up on Google, like all smart people do. So so it's up to you. All right. I'll be back in 2 minutes. I got to check on my pie. All right. Oh, which one? I don't know that there's nearly enough zeros there, Douglas. This is why scientific notation is important. I'm not counting them all, but it doesn't look like there's nearly enough. Now, it's 6:40, so we'll go over this example, and then I think we'll go on break, partially because I need to change my pie, or take my pie out of the oven. No, that is correct for the electric field. So, like I said, this wasn't a terribly difficult problem, right? So what we can look here is both of these i's are equal to each other. So on one half you have 1 over c mu naught e squared, and that's going to be RMS, and that's going to equal the power from the source over 4 pi r squared. So PR is equal to 2.2 times 10 to the third times multiplied by 3.9 times 10 to the 26th watts. Is my mic glitching out? Let me restart it. Hold on. Is that better? Okay, good. No, I think it was probably my microphone. It's been on for a while, and like I said, I'm using a very old webcam. So we multiply our 2.2 times 10 to the 3 times the power of the sun. That's the power of Polaris. That's the source power, right? The North Star. And so we can do that. 2.2 times 3.9. I don't know. I'm not my in. So it's basically 4 times 2. So it's going to be around 8. I don't know. 8.1. 8.58. Thank you. 8.58 times 10 to the 29th. Sounds about right. And we're going to be able to see that 431 light years. This one I already had pre-worked out. Is going to be 4.08 times 10 to the 18th meters. Light years are huge. So now that we have PS and 4 pi r, we can solve for E squared. I thought it would stop blinking by now. Equals PS over 4 pi r squared. To the 1/2. All right, I'm going to go fix the beeping. Hold on. I'll be back. All right. All right. Let's finish this up, and then we can go on break. No, so in order to make a pie, you have to let it rest for a couple hours. So I cook the pie now, and then I'm going to let it rest, and then I'm going to put up dinner. And by the time dinner's ready, and I'm done with dinner, the pie will be ready for consumption. Today is all about the pie. So anyway, I'll definitely have to blueberry pie. Definitely gonna have to edit that out of the video when I redo it. But anyway, let's look at this. Let's look at this expression here. So you can see we have our ERMS in terms of stuff we know, right? There's some big numbers in there, but it's not a big deal, and you get 1.2 millivolts per meter. All right. Remember, volts over meters is the. I got to take out that squared. Hold on, it's bothering me. I was writing from one expression to the other. Remember, the units for electric field is volts over meters, so this makes sense. Now, keep in mind that B, right, I always just like to write starting it this way so I don't get confused, that E over B is equal to C, which implies that B is equal to E over C. So now you can see that the B field, you have to divide this 1.2 millivolts by the speed of light, and you get 4.1 times 10 to the minus 12 Teslas, or 4.1 picoteslas. So as you can see, it's much harder to measure a picotesla than a millivolt. You would really see that if we'd gone through the lab sort of as we were supposed to. But that didn't happen, so that's too bad. But that's okay. It's not the worst thing in the world. So yeah. So that should give you the idea of how small those magnetic fields are. And so look it over, see if you have any questions, and we're going to take a 15-minute break, and we'll come back at a little after 7, and we'll wrap up. We'll get to, we're not going to finish the chapter, but we are well on our way to where I want to get to for today, so we can start next week in good shape. All right, so I will be away, and I will come back at a little after 7, and my light will be on. That'll be exciting. All right, so a little bit of blueberry exploded. That had to be taken care of. Where did I put the... Oh, man. Where did I put the pencil? Hold on. I need to find that pen. Oh, it was right there. There we go. You should not be away from your home. Pies are good. Pies are good. This one will be good as soon as the small burn I have to ice for the rest of the lecture heals a little bit. All right. Okay, so let's allow here. Okay, so moving on from this, we have a fun topic, which is radiation pressure. So radiation pressure is actually interesting, and it's a little counterintuitive because you don't think of light as creating pressure, right? You don't feel a pressure on you when you turn on the light in your room. If I shine a laser at you, it certainly doesn't push you. But that's mainly because we live in this world of friction, right? And the forces are very small. So if you were if you were in space and you had a laser light, you could actually use the laser light to very slightly move you away from an object. Because that will give you pressure. And you can see you have the absorption, the force that you have here, the two descriptions of the force, and then force is just pressure is just force over area. Because I know a lot of us didn't cover that. I'm not sure I covered it last time, but if you look back at chapter 15, you can get a nice equation here that pressure is defined as force over area. And what you can see here is that that there's a radiation pressure. So you get both the force and pressure for total absorption, and you get the force and pressure for reflection. You'll notice they aren't the same. This can create a pressure gradient, all right? So because you can reflect back more than you absorb, you can push things. So the easiest way to see this is they have these little things in museum shops that are in bulbs. So it looks a bit like this. It's like two diamonds. One's reflective, one's very absorptive, and it's usually in like a bulb that's been evacuated. So it's in a light bulb. If we could do YouTube videos, I'd definitely show it to you, but we can't do YouTube videos, so I'm definitely not showing it to you. But you've probably seen these. They just spin, and the more light you shine on them, the faster they spin. Another interesting thing about radiation pressure is you can use it to come up with a theoretical limit for how big stars are. So stars, we'll do a little aside here, stars are very massive. So stars, you can imagine, want to collapse in on themselves, right? And that's gravity pushing down. But then once they get hot enough, they have nuclear explosions pushing out. Here, let's make a better star. Let's delete everything here. We'll make a circle. Circles are good. Oh, look at that circle. A lot of stuff going on in that circle. So, or there will be a lot of stuff going on in that circle when we start drawing in it. So let's take a look here. So gravity will be green, and gravity will be collapsing all the mass into the center, and it'll be pushing inward. All right, but from the center, you have nuclear explosions pushing out. And these are for the most part equal. That's why our sun doesn't explode. Have you ever wondered it's a thermonuclear explosion, but it's not getting much bigger? That's because gravity balances that thermonuclear explosion and keeps it about the same size. Now, you can actually, you might have the question, well, how big can a star be? Well, stars can only, if stars get too big and they're too massive, the gravity works a whole lot faster, which means the fusion works a whole lot faster to make the light come out. And where this radiation pressure comes in is that as the radiation pressure is small, right? So you have this intensity over the speed of light. That's going to make that over the speed of light we've already seen is going to make things very, very small. But as your amount of light grows and becomes the size of very large stars, this radiation pressure becomes very, very big. And if you have a big enough radiation pressure, you will have not only the nuclear fusion going on in stars, but the nuclear fusion plus the large radiation pressure will not allow the star to stay stable. It'll just keep blowing itself apart. And that happens at about 300 solar masses. So the max stellar mass is approximately 300 times the mass of the sun, and it's at that point when this radiation pressure starts ripping it apart. Now, experimentally, we have not found stars over 300 times the mass of the sun, but one of the fun things about astronomy, and why I like teaching it, even though I know we're not in astronomy, is stuff always changes in astronomy. So they find some bizarre object that didn't fit with the current models of physics we have, and now we have to sort of look and see how it fits in. And it's usually a fun exercise in sort of scrambling to reorganize everything. But it's funny because even though this is not astronomy, astronomy really is the study of data we can get about the universe from electromagnetic waves. So now that you understand this stuff, you would be prepared if you wanted to be an astrophysicist. This is the basis. You need more advanced electromagnetics than this, but you could understand your basic astronomy now and how it works. You do need to get into the nitty-gritty if you want to be a professional astrophysicist, but this is the steps in those directions. For those of you thinking, oh, I can't do that, well, you can. Okay. So it's an interesting subject, but we want to skip our next main subject for this chapter. It will be polarization. And polarization is about as close as we can come to an orientation for light. Now, so basically, electromagnetic waves are polarized if their electric field vectors are directed. All right, so if they're in a single plane, we can call that the plane of oscillation. So you'll notice unpolarized light, you have random, let me go here, you have these random directions for polarization, right? They're all over the place. However, if you can vertically polarize the light, you just have light going through this one plane of polarization. And you might ask yourself and say, well, wait a minute, am I only selecting this out? What happens to the rest of the other arrows here? That's not quite true. Basically, every one of these arrows has a little bit of horizontal and a little bit of vertical. The horizontal component gets reflected or does not transmit, and only the vertical part of each of those reflects. So you can see here, this is why you'll notice that originally the light, the unpolarized light that transmits through a polarizer, loses about half its intensity. And that's because everything here averages out to you lose about half of it to the horizontal direction, and then only those vertical components will come through the polarizing sheet. All right? So essentially what polarization does is it orients the electric field lines. Okay? Now, once you have polarized light, you can actually further play with the polarization, and you can find that once you have your polarized light, if you have specifically and also a specific light beam, if the original light is initially polarized, right, the transmitted intensity through a secondary polarizer depends on the angle and the initial velocity. And the intensity of polarized light through another polarizer, I'm going to say polarizer and polarized a lot, so I'm going to get tongue-tied, is equal to this in your initial polarized intensity times cosine squared of theta. Now, where I don't want you to get confused is don't confuse this I naught. I'm going to circle them in different colors. You have I naught there, and you have I naught here. No! That is wrong. So you have your red I naught and your purple I naught. Your red I naught is your unpolarized intensity, okay? Your I naught here is actually more connected with this initial polarized I, okay? So you really want to be careful when you're solving these problems or working through polarization, okay? So any questions about this so far? Because we will have unlike radiation pressure, we are going to have a polarization example too. So if you're just waiting for an example, that's coming. Sure. Sure. This is a, what we're looking at here is sort of a compound process here, right? So if we go here, let's have light, I'll make it in blue. I think different colors would really help here. So let's say we have light go through and it meets a polarizer. We'll make our polarizers in yellow. And let's say they're orientated differently, right? So once we go through here, I'm actually going to change hold on. Let me take this off. So if we look at our I naught here in the 1/2 I naught, we're going to write that with red. So here we have I naught, right? And this process, because we're unpolarized, I'm just going to call it up for unpolarized. As we go through, the intensity after here, I, will be given by this equation. All right, I on the other side of the polarizer will be equal to I/2 1 naught. But what happens, I'm going to make just a dotted line here. What happens is that now when we get to the second polarizer, we're interested in I, the intensity, after this polarizer, and here we have an I naught in an initial polarization. So the purple, right, this I naught is equal to the red I, right? That's what I have this arrow for. So when you look at this cosine squared rule, this I will be described with this equation, because we start with polarized light, and then we have a reduced intensity, or just a pass-through intensity even, depending on the angle as we do it. So basically, in the top, you have unpolarized light to polarized light, and here you have polarized light to polarized light. Okay, so the angle is not going to make sense here because I'll have a better picture of it. But basically, if you have two polarizers, so this is your polarizer, we'll call that straight up and down. This polarizer will have some angle orientation compared to the first polarizer. Okay, and that's a little hard to draw. I have a good picture of it, but that's what this angle is here. It's an angle orientation from one plane to another. All right. Good. We're going to explore that angle a little bit more. Man, that's the second time in 2 weeks I've burned myself. That is frustrating. All right. Hold on. I may need to get another cold object. No, it's fine. So, okay. So let's go. I believe we're coming up on a practical example. So the angle, I want to write it again, I for polarized light equals I naught cosine squared theta. Now you can notice, I want you to notice here you have unpolarized light in the background. That's this polarizer. You'll notice in both of these cases it loses about half its intensity going through the sheet. And the angle that we were talking about is the angle between these two red parts here. So you'll notice in this part, theta equals 0, cosine of 0 equals 1, and I equals I naught, right? So we can see that here, that we don't actually change intensity through this polarizer. But now what I want you to notice is that we're at a right angle here. All right, so here, theta equals 90, and cosine squared of 90 is equal to 0. So I equals 0, and you'll notice that the image is completely blocked out. It's a little more subtle than that. It's the angle. The second one cancels out all intensity, right? So basically it's saying that no components go through. I don't want to say it cancels us out because we're going to see some pretty interesting stuff with polarizers where we can actually have the total angle be 90, right? But if I put another polarizer, say at an intermediate angle in between these two, you would be able to see light through here again. So it's not even that it cancels it out. But in this particular case, there's just no more components left, all right, to transmit. By inserting a different polarizer in between, you'll see that we actually we can recover some components that can transfer through. So let's take a look at that. We have in I3, you'll notice we have between I0 and I3, it's going to be a 90-degree polarization. But we'll have a 60-degree polarizer here in the middle. And so basically what happens is everything will lose its 1/2, it'll get polarized, but then everything we'll have some component, right? There will be a part that will get through and make it look like this 60 degrees. It'll sort of line through. Because remember, it's vertically polarized along the whole circle. So it's up and down, up and down, up and down. And then as it goes through, each part will construct this 60-degree planar orientated wave, and that will have components in the horizontal direction, right? So if we delete this plate, we will get 0 transmission. But now we want to do our example, and we want to see what direction the emerged polarized light is in and what the intensity is, okay? So we want to see what fraction gets through. So let's take a look. Oh, that's a cool spot there. So we want to look, we want to be sure we have everything correctly. So it shows a system of 3 polarizing sheets in the path of initially unpolarized light. So we have 1, 2, 3 points to look at. So first let's look in purple. We have I0, right? And we know that I1 is on the other side. And this will be equal to I0, or 1/2 I0. Okay? Now, when we get to our second sheet, right? This one is orientated at 60 degrees. So this is, hold on. We're going to call this theta equals 0. And then we'll call this theta equals 60 degrees. All right, and here we can see that we have I1 on this side, right? As we go through, we have I1, and on the other side we have I2 is equal to I1 times cosine squared of 60. All right, you can put that in your fancy calculators and figure out what this number is. And then we can go to our final polarizer, which I'll put down here. And you'll notice you start off here with I2 on one side, and that will equal I3 will be your final polarization, and that will be equal to I2 cosine. What angle are we going to put here? What is theta going to be equal to in this example? 30 degrees. Very good. Because remember, it's the angle from the previous polarizer, right? Not the total angle from the initial. Now this is 0. It turns by 30. So we can see here, we cosine squared 30. So all you have to do is sort of plug in each thing, right? I1 can go here. You get that's equal to 1/2 I0 cosine squared 60. And so you can plug in for I2 here. That's going to be equal to 1/2 I0 is going to be equal to cosine squared 60 times cosine squared 30. And that should give you your polarization angle. And you should note that the answer, what you want to note here is what is I3 over I0. And so this will give you 0.094. Yeah, no, 10 times. So in the end, you get I3 equals, yeah, I0. Not quite. You should get, you're off by an order of 10. Because it should be 9.4%, not, it should be 0.094, not 0.993. It should be 0.09375, not 0.9375. All right, that makes sense. So, and now we can look here, but we see the final polarization gives us our direction, right? It's polarized in this horizontal direction, because that's the component that lets things pass through. Okay? So by inserting a polarizer, by adding something to the system, instead of having 0 light go through, now we'd have a little less than 10% of the light go through. And if you look at the previous slide, if you add that polarizer at 60 degrees here, you get 10% of the transmission come through, and you'd be able to barely see the words polarizer written in this part of the frame. I mean, in this part of the frame. Yeah, Mustafa? .09 is fine, just depending on where you cut off and did your rounding. So I don't get how light can get through the second polarizer. Well, you have to remember, it goes angle by angle, right? So if it's just these two, if it's just this one and the one at the end here, you have, you only have vertical polarized and you have no horizontal component, so nothing gets through. But now when you add the second polarizer, you have this vertically polarized, right? But you can't think of it as just one line coming through. You think of it as the circle here. And as the circle comes through, all these little bits will shine through to create 60-degree polarized lines, right? And what we'll get through is a electromagnetic wave whose electric field orientation is on this 60-degree plane, all right? That's what it'll look like. It'll look chopped up a bit, but that's what it'll look like. And so when it meets the horizontal polarizer, that now has a horizontal component. So that horizontal component will just go through, and the vertical one will be blocked. It's weird. Polarization is weird. It's one of those, you start to see that weirdness in physics happens with waves, it's not just quantum physics, but classical physics can be a little crazy too. And polarization is sort of a very good counterintuitive example of that. It seems like no matter what you should add, if you start with 0 and end with 90, you should get the same thing, but you're not. No, this isn't like an interferometer. I mean, an interferometer is more like a beam splitter where you send one intensity going one way and one going the other, right? So a beam splitter is a different thing. The polarized light is still just considered one light beam going through. Now you can, what's interesting is you can actually split light, right, in a beam splitter and then polarize one end and not polarize the other and use that as part of your interferometer. That can get a little interesting. But yeah, we're not really splitting a photon or a wave thing here, or doing interferometry. I'm not sure exactly what you're talking about, Lewis. Then, if it's a gold piece of gold, when they did quantum physics, they were able to shoot things through thin gold sheets and get electrons to bounce back, straight back, essentially showing that that since most of them went through, the idea there was that the nucleus was all concentrated in one area and not spread out as was previously hypothesized. So I'm not sure what specific experiment you're talking about. So you might have to help me out after class or send me a link or something so I can look at it and be sure I know exactly what you're talking about. Okay. So let's move forward. So now we want to introduce reflection and refraction. So I want to introduce some of the basics here, and we'll probably start next week with a problem to sort of wrap it up. Just want to see where I am here. So we're moving along. So this is sort of the last major topic, I think. I think there's another one. But yeah, total internal flight. That's part of this, though. So we will talk about some interesting things. Now, I wish I had this here to talk about reflection and refraction, some demonstration like this. We usually have a pretty good demonstration in the class, but this is one of those moments where one thing, I think my least favorite part about doing this online is a lot of the fun demonstrations that are fun for me, I can't do. So I get kind of bitter whenever one comes up. So we have some nice blocks to show this with and laser light. We can actually see this whole reflection refraction business happen. So basically what we're looking at is light through other mediums. Now, we've talked about the speed of light, and the speed of light is constant in a vacuum, but the speed of light does change in mediums. All right, and the way it changes in mediums are materials are understood to have a property called the index of refraction, n. And the C, so n for a vacuum is about 1. N in air is also about 1. We call that vacuum, call that air. But if you're looking at C in material, it's equal to C vacuum over n. Okay? So you can definitely slow things down in a material. And while you cannot go faster than the speed of light in a vacuum, fun fact, you can actually go faster than the speed of light in a material. All right? This happens frequently in nuclear reactors, and you get like this weird light cone shockwave thing. It's pretty awesome. So we can see here, a photograph shows us an incident beam of light, and it shows some of the light reflecting off the water and some of it transmitting through the water. And you'll notice we can describe those with an angle. So we have our angle of incidence and our angle of reflection. And the law of reflection, which you should have learned a little bit of in Physics 1, will tell you that the angle of incidence is indeed equal to the angle of reflection. All right? Both relative, not to the horizontal, though, in this case, but relative to the normal. All right? So your angle will be with respect to this symmetry axis of the material. All right? That includes both materials. And you'll see here you have your incident ray, and these ticks represent plane waves at some angle theta, and you'll have this angle of reflection that will be equal to it. But now where things get a little more complicated, right? That's going to leave a mark. Where things get a little more complicated is this refracted angle. All right, and we can use something called Snell's law, which is this expression here, to figure out the angle of refraction. So if theta 1 is in a medium 1, so that's we're in here, right? Say we're in air and n1 equals 1, then theta 2 will be equal to, or sine theta 2, probably cleaner to write, will be equal to n1 over n2 times sine of theta 1. All right? And from here, you can get that, that index of refraction. All right? Or that angle of refraction. Okay? So next time, we're going to definitely want to do some stuff with Snell's law. We're going to do some examples. And we're going to go over these 3 cases. And I think I'm going to stop here for tonight because this needs about 30 minutes. We have about 15 minutes. So I'm just going to stick around and answer questions. And if something comes up and to talk about lab or anything that's being bothersome, I want to be sure we can do that and clarify anything that might be confusing. But I am going to turn off the recording, and we'll start here, not tomorrow, but on Tuesday, after our review.